Till now we have looked at what are dislocation interactions. Now we will be looking at what are dislocation intersections, and we'll get introduced to terms such as jogs and kinks. These jogs and kinks are nothing but a break in the dislocation line, and this break in the dislocation line are nothing but defect in the dislocation lines. Now let's look at how these breaks have been created on these dislocation lines. So we have slip plane, and let's mark a dislocation, an edge dislocation, whose dislocation line is marked here, and a Burgess vector is along this way. And let's create a break on this dislocation line. So we can create a break on this dislocation line in this way, where there is a break here on this dislocation line. And if you see that this break is not on the original slip plane. So you have a dislocation line segment line on this slip plane 1, and another part of this dislocation line is on slip plane 2, and where the break is not on the slip plane. That is, it is on the plane which is not a glide plane for this dislocation. And such breaks are called as jog. So jogs are dislocation line segments or breaks which are out of the original slip plane. So this dislocation break, or this break in the dislocation line, is out of this original slip planes, and such breaks are called as jogs. There is another way of making a break, and this break is shown over here. So you have a break in this dislocation line, and you can see that this break in this dislocation line stays on the same slip plane. And such kind of breaks on this dislocation line are called as kinks. So these are kinks, where dislocation line segment or a break remains in the same original plane or a glide plane. And these breaks are nothing but an extra segment in the dislocation, and thus they increase the energy of dislocations. So these breaks increases the energy of dislocation. We know the energy of dislocation per unit length as to be alpha gp square, and if you try to evaluate what is an energy of this jog, so you can say that energy of jog can be equal to alpha gp square into b1, where b1 is nothing but the length of this jog. So this length of the jog or these breaks increases the energy of a dislocation. Also, these breaks in this dislocation line impede motion of the other dislocations, and thus they result in the strain hardening. Now, how these breaks forms on these dislocation lines? So this break forms on the dislocation line because of intersection of dislocations. Now let's look at this jog and kink in more detail. So here we have shown jog and kink, and you can see this is a dislocation line, and there is a break in this dislocation line. So let's mark that you have a glide plane here, and you have a glide plane here, and this break is on the other plane which is not a glide plane for this dislocation, and such breaks in the dislocation line are called as jogs. And kink are a break in dislocation lines which stays on the same slip plane. Let us mark that here. So you have a glide plane, and this break remains on this same slip plane. So this kind of breaks on the dislocation line are called as kink. Now, if you take any standard textbook and find out what is jogs and kinks, so the breaks on the dislocation lines in most of the textbook are referred as jogs. Let us write that down. So breaks on dislocation lines are called as jogs. And kink is a special case of a jog. So what do I mean by that? So all the breaks on the dislocation line are called as jogs, and when these jogs remain on the same slip plane or a glide plane, these are called as kinks. Let me put it in a set format. So you have jogs, and kinks are nothing but a subset of these jogs. So these are kinks, which are special case of jogs where breaks on this dislocation line stays on the same glide plane. Now how these jogs and kinks form, as I mentioned you earlier, this form when there is an intersection of dislocations. And there is a rule which says that how these jogs and kinks should form. So when two dislocations intersect, each acquires a jog equal in direction and length to the Burgess vector of the other. Let us read this again. When two dislocations intersect, each acquires a jog equal in direction and length to the Burgess vector of the dislocation, other dislocation. So now let's understand this using some examples. So let's consider these two planes and let's consider an edge dislocation with a Burgess vector pointing in this direction, and let's consider another edge dislocation in this slip plane with a Burgess vector pointing towards down. And if you look at these two cases carefully, you have these edge dislocations having Burgess vector b1 and b2. So these Burgess vector b1 and b2 are perpendicular to each other. Now when these two dislocations intersect, how they will intersect, let's see that this term moves along this direction and this dislocation moves down. And when it intersects, the rule says that this dislocation, when they intersect, each will leave a step or a break on the dislocation line along the direction of the Burgess vector of the other, and the magnitude also will be the magnitude of the Burgess vector of the other. So let's see this, and if you apply this rule on this dislocation, which is B2, so you can see that there is a step created on this dislocation B2 along B1 direction. So this step is along B1 direction. Let us mark here. So this is along B1 direction, and what will be the magnitude of this step? So the magnitude of this step also will be equal to the Burgess vector of this dislocation, that is B1. So this magnitude of this step will be B1, and this kind of steps which are moving out of the glide plane are called as jog. So you have a jog formation on dislocation B2 because of the intersection with dislocation B1. And what will be the break on the dislocation B1? Let's look at that also. So here there will not be any break created on this dislocation B1. Why? Because the Burgess vector B2 is parallel to the tangent vector of this B1. Let's look this condition. So let's mark the tangent vector for B1. So this will be tangent vector T1, and this T1 is parallel to B2, and thus there will be no steps or break on B1 this dislocation. So there will be no steps created on this dislocation. Now let's look at what is the nature of this jog. So to find out the nature of jog, we need to find out what is a tangent vector and a Burgess vector for this break or a jog. So let's find out the tangent vector. So the tangent vector for this dislocation I am marking here. So you have tangent vector T2, and as we know that this Burgess vector for this dislocation will remain invariant. So this Burgess vector will be always along this direction. Let us mark that. So it will have a Burgess vector B2 in this direction. So this T1, T2 is perpendicular to B2, and thus this jog has an edge character. So we have a jog created because of the intersection of two dislocations, or you can say that the jog created on B2 because it intersected with dislocation B1, and that has an edge character. So let's understand this again. So we have this dislocation B2 which is get intersected by this dislocation B1, and the jog will form along, or the break will form on this dislocation line along B1. So we have a break on this dislocation line along B1, and what is the magnitude of that break? That magnitude of that break will be magnitude of this Burgess vector B1, and these breaks are called as jog. Now to find out the character of this jog, what we have done, we found out what is a tangent vector of this dislocation, and the Burgess vector remains invariant for this dislocation. So this T2 is perpendicular to B2 and thus it has an edge character. Now let's look at another condition. Let's look at these two screw dislocations. This is a dislocation line which is marked by this red line and blue line, and the Burgess vectors are parallel to these dislocation lines. These are screw dislocations. And if you look at this case carefully, so this will be a screw dislocations having Burgess vector perpendicular to each other. Now let's see that this dislocation B2 moves in this direction and B1 moves down, and let's see when they intersect each other what kind of breaks they form. So on B2 there will be a break because of intersection of B1 dislocation. So the break will be along B1 direction. So this will be along B1 direction and magnitude will be equal to that of B1. So we have a break on B2 along B1 direction with a magnitude of B1, and this kind of breaks are called as jogs because this break is not on this same slip plane or a glide plane. So such kind of breaks are called as jogs. And now let's consider what will be the break on this dislocation B1. So it will have a break on this dislocation B1 because it intersects dislocation B2. So it will have a break along B2 direction. So it will have a break along B2 direction with a magnitude of that break will be B2. And this is nothing but a jog. So this is not glide plane for this break, or so this is a jog because the break is moving out of this glide planes, and thus you have a jogs formation when two screw dislocations having Burgess vector perpendicular to each other intersect. Now let's find out what is the nature of these jogs. To do that, what we have to find out what is a tangent vector and a Burgess vector. So let's look that also. So I'm marking a tangent vector for B2 and it is in this direction, and Burgess vector will be invariant for this dislocation and it will be in this direction. So you can see that the tangent vector T2 is perpendicular to B2. So this is nothing but an edge character. So you have an edge character of this jog which is formed on this screw dislocation. Now let's look at what is the nature of this jog which is formed on dislocation P1. And to do that we have to find out a tangent vector and a Burgess vector. So let's do that. So let's find out a tangent vector. So you have a tangent vector along a dislocation line which is going like this. And what will be the Burgess vector? The Burgess vector remains same. So it is B1 here. Now you can see that the tangent vector, that is T1, is perpendicular to B1 and thus it has an edge character. So these jogs which are formed on the screw dislocations has an edge character, both jogs. So we have screw dislocation, but the jogs which are formed on them has an edge character. So this edge character cannot move on any slip plane and thus it stops the moment or motion of these dislocations and thus it results in the strain hardening of the material. Now let's look at some other cases. So let's look at these edge dislocations having Burgess vector B1 and B2, and in this case you can see that Burgess vector B1 is parallel to B2. Now let's see when they intersect what kind of breaks they form. So let's see that this dislocation is moving along this direction and this dislocation is moving along this direction. So when it intersect with B2, the break will be on B1 will be along B2 direction. So it will be along B2 direction with a magnitude of this purchase vector. So let's mark it here. So you form a break along B2 direction with a magnitude. So magnitude of this step will be B2. And now let's look at what's the step on this B2 dislocation. So we have a step which is created on B2 which will be along B1 direction. So this step which is created along B1 direction with a magnitude equal to B1, and let's find out what is the nature of these breaks. So these breaks are on the same slip plane for both B1 and B2, and thus these are nothing but kinks. So these are kinks, and these kinks are formed, that is, these kinks are formed by because B1 and B2 intersected each other. And let's find out what is the nature of these kinks. Let's find out the nature of kink formed on this B1 dislocation. Let us find it out. So to do that, we find out what is a tangent vector. So we have tangent vector varying in this way. And what's the Burgess vector? So Burgess vector will remain invariant for this. So it will be along this direction only. So we have tangent vector T1 which is parallel to Burgess vector P1, and thus it has a skew nature. So this kink has a skew nature. So this is an edge dislocation, and the kink formed on it has a skew nature. Similarly, let's find out what is a nature of this kink on the dislocation B2. To do that, find out what is a tangent vector. So we are finding out a tangent vector here. So tangent vector is in this direction, and B2 will be along the same direction. So we have T2 parallel to B2, and thus this is also a skew nature. So this kink which has formed on this B1 and B2 has a skew nature. Now let's look at another condition. Now let's look at an edge dislocation B2 and a skew dislocation B1, where you have B1 perpendicular to B2, skew and edge nature of these dislocations, and B1 is perpendicular to B2, and let's see that this moves in these directions, and let's find out when they intersect what they form, what kind of breaks they form. So for B1, the break will form along B2, along the direction of B2. So it has formed along the direction of B2 with a magnitude equal to B2, and thus this is nothing but a kink because this break is on the same slip plane. Now let's look at for B2. So you have a break which will form along B1 direction. So you have a break which has formed along B1 direction with a magnitude equal to B1, and thus this break is out of this slip plane, and this is called as a jog. So you have a jog formed on this edge dislocation, and you have kink formed on this skew dislocation. Now let's find out what is the nature of this jogs and kink. Let us find out for a jog. First, let us find out for a jog. So let's find out what is a tangent vector. So we have tangent vector T1, and you have a Burgess vector B2. So we have a Burgess vector B2 which is perpendicular to this tangent vector, and thus this is a edge nature. Similarly, let's find out what is a nature of this break or kink which has formed on this dislocation B1. So you have tangent vector going in this way for this dislocation, and you have a Burgess vector which is along this way. So you have tangent vector T1 parallel to Burgess vector B1. So this is screw nature. So the kink which has formed on this B1 has a screw nature. So these were some of the cases which we have seen when dislocation intersect, how the kinks and jogs form and what are their natures, whether they are of screw nature or an edge nature. Now let's see how this movement of jogs takes place. So we have seen that the breaks on the dislocation line are called as jogs, and now let's see how these jogs move. So we have seen this case where you have a screw dislocation here. Let's consider this segment, which is this is a screw nature. This is also has a screw nature, but the break on this, that is PP dash, has an edge character. So let's find it out how we are finding out the nature of this break. So we have a tangent vector which is going in this way, and you can see this is a screw nature where we have a Burgess vector in this direction. So these are screw. This is a screw dislocation, and it has formed a break on this. So you have a Burgess vector along this direction. So you have a Burgess vector along this direction, and the tangent vector is perpendicular. So the PP dash has an edge nature. Let us write that down. So PP dash has edge nature. Now when this dislocation, screw dislocation, want to move or glide on some plane, as you know that this PP dash cannot glide on any plane because it has an edge nature. So this PP dash can glide on this plane, that is PP dash R, but it cannot glide on this PP dash Q dash and Q. So this dislocation has to move along this direction. What it has to do, that this break which has an edge nature has to climb, because this cannot glide, because this is not a glide plane for this PP dash, which is a break, which is nothing but a jog on this screw dislocation. Why it cannot glide on this plane, that is P dash, Q dash and Q? Because the Burgess vector and the tangent vector doesn't lie on this plane. So for an edge dislocation to glide on any plane, what is the condition? That the tangent vector and Burgess vector should lie on that plane. So this jog can glide only on P dash, R dash and R plane, but it cannot glide on P dash, Q dash and Q. Thus, if I want to move this dislocation along this way, what it has to do, we have seen that when an edge dislocation has to move on some other plane which is parallel to it, it can do by climbing. So there must be a climb here occurring. So we have to climb this edge dislocation along this direction to move this screw dislocation to this position. So thus, if it would have been just a screw dislocation, it can glide on any slip plane. But now there is a break which has been created, that is a jog on this screw dislocation which has an edge character. It cannot move so freely. So thus, the movement of this screw dislocation is impeded because of the formation of such jogs on this screw dislocation. And if it has to move, it has to move by a process of climb, and the climb involves formation of vacancies. And thus, the movement of this kind of screw dislocation becomes difficult. Now let's look at how this movement can occur. So this movement can occur like, let's say this is a jog which has an edge character and has to move forward in this direction. What it does is it forms vacancies. So these jogs on this screw dislocation which has an edge nature, if they want to move forward, there will be formation of vacancies. And these jogs act as a source or sinks for vacancies when they move under the influence of stress or temperature. Now let's look at this condition. We have seen this when edge dislocation has to climb. So we have seen a dislocation line here. Now on this dislocation line there will be a vacancies, and this dislocation line is now bent over here. Let me write that down. So this dislocation line has moved like this because of the vacancy formation or vacancy accumulation at this region, and this region here, this part is called as jog in this dislocation line. Let me mark that also. So these are jogs. These are jogs. So these jogs can move when there is a vacancy accumulation over here, and you can see that as the vacancy get accumulated at here, you can see that the dislocation climbs up. So dislocation climbs up, and we have seen this scenario when the vacancy joins an extra half plane, the dislocation can climb up. And when this vacancy joins this extra half plane, there is a formation of jogs. So as I mentioned you, the jogs can move by climb process, and this climb process involves accumulation or annihilation of vacancies. So formation or annihilation of vacancies takes place during the climb process of these jogs. And this involves a stress and thermal activation. That is, the climb process involves the stress and thermal activation to move these jogs. So this is an important thing which we have seen for jogs and kinks. And with this, I will stop here.